The next paper in this direction, it was by Marshall Hall in 1943. Again, it was related with something with projective geometry in the title. But he proved a theorem which I want to mention, that if D is a division ring, and xy minus yx squared z minus z xy minus yx squared equals 0 for all x, y, and z in D, then the division ring D is either commutative or four-dimensional over its center. This means that D is either commutative or something like the quaternion algebra. So I think that after this there were a lot of theorems, and the theory started to, in a purely algebraic way. I don't want to do further history. There is a very nice survey article by Mitsur about this. And now I want to give the formal definition. So the formal definition, this is, I fix K to be a field of any characteristic. And I consider associative K algebras only. The existence of unit is not so important in the general case. So in the moment I don't assume that the ring has a unit. And Kx, which is K, x1, x2, etc. This is the free associative algebra over K. So if you can think of this as the algebra of polynomials in the non-commutative variables x1, x2, etc., etc. So you simply make difference between x1, x2, and x2, x1 when you speak about polynomials. And we say that if R is an algebra, so this is the definition, if R is an algebra, and f x1, xn is a polynomial from the free associative algebra, we say that f is a polynomial identity maybe I write here f equals 0, but I put f equals 0 in parentheses because you call also f itself and f equals 0 an identity. So this is something which is not, I'll continue the definition. If f of R1 Rn equals 0 for all R1 Rn in R. Formally you can state this in the following way. So this is equivalently f x1 xn is in the kernel of all homomorphisms from the free algebra to R. So if you prefer this definition is also okay. So you have some polynomial in non-commutative variables. If it vanishes when you replace it by arbitrary elements from the algebra R, then this is called a polynomial identity for the algebra R. For the algebra R, of course. But you know that the free algebra has such a universal property similar to the universal property of the polynomial algebra. If you send the set of generators to some algebra, you can extend this in a unique way to a homomorphism. So this is equivalent to say that this is the kernel of all homomorphisms. And now, the first obvious example. This is the case when R is commutative. When you have that xy minus yx equals 0. Okay, sometimes I write, instead of x1, x2, etc., I write xy, z, etc. And this expression is so popular in mathematics that it has a special notation. This is the commutator of x and y. And, of course, commutative algebra, they satisfy an obvious polynomial identity. Not so obvious, but also not too difficult to see, is the case when the algebra is finite dimensional. So if the algebra R is of dimension less than n, you have such an expression which is, Sn in n variables. This is a sum with the sign where sigma is from the symmetric group, and you have here x sigma 1, x sigma n. And this expression equals 0 because this is something like a determinant. When you have two elements here equal, this vanishes. And of course, since this is linear in each variable, it's a linear combination of elements of the base. When you base here elements of the basis, and it's an exercise to see that this is 0 for algebras of dimension less than n. And this polynomial is called the standard polynomial, or the standard identity. There are also some other examples. One of them, this is the Grassmann algebra. Maybe I write the Grassmann algebra here. So the Grassmann algebra, or also called exterior algebra, it is generated by some elements E1, E2, etc. Yeah, the generators. The defining relations there, that if you have EI, EJ, this is minus EJ, EI. So they anti-commute. So these are the defining relations. And to make this algebra not commutative, we assume that the characteristic of the field is not equal to 2. Because otherwise you get a commutative algebra. And the Grassmann algebra, it is known that E, I denote this by E. E has a basis consisting of all products where E1 is less than E2 less than En. The first part, that the Grassmann algebra is spanned by such elements, it's easy because here you have EI equals minus EI. So you have twice EI equals 0. So you have that EI squared equals 0. Also here you can rearrange the variables, but the difficult part is that these elements form bases. So this is easy that EI1 EIN span the Grassmann algebra, and to say that this is a basis, this is difficult. And this is a basis. Of course, in the standard courses of algebra, this is proved, but this is not obvious. For example, if you want to give some exercise on Gröbner basis in the non-commutative case, this is a good example to do this. And the Grassmann algebra has the following property, that if you take two elements, EI, EJ, and you want to commute with another element, EK, so this is the commutator, this is EI, EJ, EK, minus EK, EI, EJ. You take this element and you put this here, you change the sign once. So you get EI, EJ, EK plus EI, EK, EJ. Now you change the place of these two elements, you change the sign once again, and you gain EI, EJ, EK minus EI, EJ, EK, which is 0. So this means that the elements of length 2, or the elements of even length, are central. And now you take three elements R1, R2, and R2, and R3, and you want to evaluate, from the Grassmann algebra, you want to evaluate R1, R2 the commutator, and the commutator once again. Of course, these elements, they are products, they are linear combinations. R1, this is a linear combination of something like some alpha I, EI1, EIP. R2, this is a linear combination, some BJ, EJ1, EJQ. R3, this is some linear combination of gamma K, EK1, EKS. And if you take the commutator of these three elements, this is a sum. Here you have alpha I, beta J, gamma K, and you take the commutator of only of these elements. AP. So this is sufficient to evaluate only the elements from the basis. And you see, if this is not 0, the inner commutator, this means that both P and Q are odd, the length of the word. Because if one of them is of even word, of even length, you get 0. Because the even, you have that the elements of even length, they are in the center. So the only way you have, when this is not 0, you have that P and Q are both odd. And in this case, of course, P plus Q, the length of the word, is even. And you get that this is 0. So this is some example of an algebra which is not finite dimensional, and nevertheless it satisfies a polynomial identity of degree 3. I didn't say in a definition, but maybe I have to add this now. Maybe here you may add this simply in the corresponding place, that if R satisfies a non-trivial, it is different from 0, polynomial identity, then R is called a PI algebra. So after having some examples, during these 4 lectures which I have, I will try to prove that PI-Algebras, they are sufficiently good class to be studied, which in some sense is similar to the class of finite dimensional algebras. And they enjoy many of their properties, also the properties of commutative algebra.